This is S. Patil, Assistant Professor in the Department of Physics, Yashwantrao Chauhan Institute of Science, Satara. Here we are going to learn about Stark effect, one of the important application of time-independent perturbation theory in quantum mechanics. So let me start Stark effect in quantum mechanics. When a static electric field is applied to an atom, the spectral lines will split up, and this effect is known as Stark effect. This effect was first observed by a German physicist, Johann Stark, in 1913. So, as we know, there are number of orbits around the nucleus of atom. Every orbit have the energy value different from others. As we know, n is the principal quantum number. The energy of that orbit varies with principal quantum number. Hence, the outer orbit have higher energy and inner orbits have lower energy. When an electron makes transition from higher energy orbit to lower energy orbit, it will emit the photons, and we can observe these photons under spectrometer. We will observe here spectral lines in a spectrum. Now, if we place this system under the influence of electric field, then observed spectral lines will split up due to the electric field influence on the dipole moment due to the charges. We know that nucleus have positive charge where electrons have negative charge, and applied electric field will interact with this dipole moment, and due to which there is splitting of spectral lines, splitting of the energy levels is observed. So we will study this effect by the perturbation theory. So in case of perturbation theory, we know that H is equal to H0 plus H dash, where H0 is unperturbed Hamiltonian and H dash is perturbed Hamiltonian. In case of hydrogen atom, unperturbed Hamiltonian will be the kinetic energy plus potential energy. The kinetic energy is p square by 2m and potential energy is minus e square by 4 pi epsilon 0 r, where H dash will be the perturbed Hamiltonian. This perturbation is due to the electric field which is applied on that hydrogen atom. And here, if E bar is the electric field, then minus E R bar dot E bar is the perturbed Hamiltonian. So we can write this dot product here as minus E R E cos theta. So this is about the perturbation theory. Now we'll go to the first order Stark effect for ground state of hydrogen atom. As we know, the ground state of hydrogen atom means the principal quantum number value is 1. When the principal quantum number n is equal to 1, at that time L value is 0, because L varies from 0 to n minus 1. So L equal to 0. And ML, the value of ML is also 0, because value of ML varies from minus L to plus L. So there is a set 100 with principal quantum number, orbital angular momentum quantum number, and magnetic momentum quantum number. So as we know, the first energy level or first orbit have energy minus 13.6 electron volt. When the atom, the hydrogen atom is in ground state, at that time that single electron will be in the first orbit only, and hence the energy is minus 13.6 electron volt. So this is the ground state of hydrogen atom. Now for this ground state of hydrogen atom, there is only one state where 100 state. Now I refer here 100 NLML values. 100 state only have minus 13.6 electron volt value, and hence this is non-degenerate case. Why it is non-degenerate? There is no degeneracy. If two or more than two states having same energy at that time, we can say it is a degenerate case. In case of non-degenerate theory, we have the energy correction formula E dash is equal to psi star h dash psi. That is integration of psi star h dash psi d tau. By using this formula, we can find the correction to the energy for non-degenerate case. So now we have value of psi. Psi is for 100. So let we solve this integration, then we will get directly the correction to the energy due to the perturbation, due to the applied electric field. So main unperturbed energy is minus 13.6 electron volt. Now we will find E dash, and we will add this E dash into the En. Okay. So now here E dash will be equal to integration of psi star h dash psi d tau, where we have 100 state. So 100 means what? 1s orbit, 1s level, and for 1s orbit 100 state, we have the wave function for hydrogen atom is square root of 1 upon pi a naught cube e raised to minus r by a naught. In this way we have 200 state, we have 210 state, that is 2p, and so on. So by using these wave functions, we can find out the integration. So this is the value for E dash. For E dash, we have calculated here, the value is 0. So if the value of correction to the energy is 0, we can say that there is no correction, or correction is 0. There is no splitting for ground state of hydrogen atom. Okay, now we will go to the next part, that is first order Stark effect for first excited state of hydrogen atom. So when we talk about the first excited state, that means n equal to 2. For n equal to 2, principal quantum number is 2. L values will vary from 0 to n minus 1, that is 0, 1. There are two values of L, 0 and 1. So for each value of L, there are ml values. For L equal to 0, ml value is 0. For L equal to 1, ml values will 1, 0, minus 1. So now we have the various states, and each state have energy minus 3.4 electron volt. This is energy for n equal to 2, minus 3.4 electron volt. So now we have the various state: 2, 0, 0 state, 2, 1, 1 state, 2, 1, 0 state, and so on. So this is the first one. We can say it is 2s, then 2p, and so on. So with this, we have 4 different states having same energy minus 3.4 electron volt. And here we can say this is degenerate case, because there are various states having same energy. So when we talk about the degenerate case, at that time, to find out the corrected energy, we will have E dash is equal to H11, H12, H13, H14 and so on. With this manner, we have to solve the correction to the energy for degenerate case. So H11 means what? H11 means 200 H dash 200. What is H12? 200 H dash 210. What is H13? 211 H dash 200. In this way, we can find H11, H12 and all of 16 integrations we have to calculate, and then we have to substitute the values of all H11, H12 and so on here in this determinant. Then we have to solve this determinant, and easily we can find value of E dash, that is the correction to the energy for the first excited state of hydrogen atom. For first excited state, the energy which is unperturbed energy is minus 3.4 electron volt. So let me find by using this formula correction to the energy. So we have these formula. So when we take the integrations and when we solve H11 by using those wave functions, we will get answer is 0, and the most of values from that 16 will be equal to 0. Only non-zero terms are two. One is H12 and H21. H21 and H12 will be the non-zero values, and other than these are zeros. So now we can make some changes by transferring the E dash to the right hand side at the diagonal elements, because when we shift this E dash, it will becomes minus E dash, and now we can easily find what is the E dash square. So, or what is the value, what are the values of E dash. With this, now we have E dash square dot into E dash square minus 3a naught E whole square is equal to 0. And if you solve this equation, you will get the 4 different values of E dash, because here there is E dash raised to 4 is there, and hence we will get the 4 different values. 4 by 4 determinant is there, so we will get the 4 different E dash values. Here it is E dash equal to 0, first value. Second value is also E dash equal to 0. Third value will be E dash equal to plus 3a naught EE, and fourth value is minus a naught 3a naught EE. These are the 4 different values of E dash. E dash is the correction to the energy for first excited state of hydrogen atom, where unperturbed energy is minus 3.4 electron volt. So with this, we can explain the Stark effect. So for n equal to 1, unperturbed energy is minus 13.6 electron volt, and when we apply the electric field, there is no shifting of energy, and hence we know that its correction to the energy value is also 0, hence there is no splitting. When we talk about the n equal to 2, here we have the energy is minus 3.4 electron volt, and this energy level will split into the 4 different parts. 2 parts have 0 correction and 2 parts have non-zero correction to the energy, which is 3 a naught EE. Here it is plus 3 a naught EE, and here it is minus 3 n0 E correction to the energy. So the spectral lines will split up, which explains the Stark effect. I hope you understood this Stark effect. Thank you.